Welcome to the PhotoModeler Scanner Basic Project tutorial. In this tutorial, we will show the creation of a basic PhotoModeler Scanner project from start to finish. We start a new points-based project. Select our images and add them to the project. Our images are automatically matched with a camera from our calibration library. This sample project is a boot print in some sand. Next, we run Idealize on these images to remove any lens distortion, uncentered principal point, and ensure the pixels are square. We'll skip to the end of the Idealize process. How long this takes will depend on the size of the images, the amount of RAM, and your CPU speed. Once the project has been idealized, we will save it as idealized.pmr. You can see the borders of our images are now padded with black to account for the lens distortion that has been removed. Any lines or edges that are straight in real life will now be perfectly straight in the image, and any off-centering of the principal point will have been corrected. Next, we will use auto marking to identify the coded targets. Since the background sand in the project has a lot of natural noise, we mark each of the 4 coded target strips as individual regions. This will speed up the marking and remove the chance an area of sand is misidentified as a target. Now, we'll mark the second image. Once our targets are marked, we can process the project. This dialog warns us that the angles between our 2 photos are low. Unlike regular PhotoModeler projects, PhotoModeler Scanner projects require low-angle stereotype photos. In this case, we can proceed with the low angle check disabled. If you are unable to use targets, you will need to make sure your manually marked points are well placed, as a good orientation is important when generating point meshes. Our project is solved and our residuals are low. To make the units displayed on the dense surface dialog match the real world, we need to set a scale. The distance between these 2 points is 161 millimeters. You can define the area used to generate a point mesh in 3 ways: by drawing a 2D trim on one or more of the photos, by defining and selecting a surface, or by using the whole photo extents. In this case, we will add a DSM trim to surround the area of interest. We switch to DSM trim mode and zoom in to mark our area of interest. Right-click and finish the trim. DSM trims have 2 properties: a checkbox for if it is enabled or not, and a setting to indicate if the area inside the trim should be used or if the trim indicates a hole and no data inside the trim should be used. Now that we have our trim set up, we'll save the project as with trim. We open the Create Dense Surface dialog. The information at the top gives an indication of the project's quality and if it is suitable for generating a point mesh. Your project must be solving well and have low residuals. The trims and surface information defines what extents and approximate starting point the dense surface algorithm will use. The base to height ratio shows the min and max of the base to height ratio for all selected photo pairs. In this case, our project only contains 2 photos, so the base to height for the pair is displayed. Ideally, projects should have a base to height ratio between 0.1 and 0.6. This next section shows which set of photo pairs will be processed. Since there are only 2 photos in this project, there is only 1 pair available. The settings section shows what values will be used during point mesh creation. When you select an item, a description of the parameter is displayed below. You can increase or decrease the size of this window so that you can see the full description. For sampling rate and depth range, there are also hyperlinks to recalculate the default values. Sampling rate controls approximately how much space is between each point in the mesh. In this case, PhotoModeler Scanner will try to create a point every 3.5 millimeters, or about every 0.14 inches. The larger this number, the faster the point mesh will be to create, but also the sparser the point cloud will be. Extents from controls what area of the image will be used when creating the point mesh. In this case, we can choose between the DSM trims, which is the DSM region we defined, or the whole photo. If we had added a surface and selected it, we would also have the choice of defining the extents as coming from the surface's area. Depth range controls how far above and below the approximate surface the point mesh algorithm will search. When you have a surface selected, the height specified is the distance above and below your surface. In this case, as we have no surface selected, an implicit surface will be created using the points in the project. As our points are mostly on one plane, the implicit surface created will be that plane, which is a reasonable approximate surface for this footprint. If you decrease the depth range, less data will need to be processed, so it can speed up the point mesh creation. It also limits the search area, so reduces the chance of an incorrect point location being identified. However, if the depth range is too small and the valid location lies outside the search range, it can never be found, and as a result, there is a good chance an incorrect location will be matched, resulting in noise. The troubleshooting tutorial shows an example of this. The advanced parameters can usually be left at their default values, but the troubleshooting tutorial shows some cases where you may want to adjust them. Subpixel controls whether the matching is done on an integer pixel basis, or for more accuracy, at a floating point, less than 1 pixel basis. Supersampling controls how the subpixel sampling works. If you find ripples or waves in the data increasing, this value may help reduce it. The matching region radius defines how large the search area window is. With a radius of 7, a region of 15 by 15 pixels will be used when comparing data between the 2 images. Depending on how random the pattern on your object is, you may need to increase this number if points are dropped out. The larger the window, the slower processing will be, as it needs to compare more pixel data. Texture type controls how strong a match needs to be before it is thrown out. If your point mesh has little or no noise but lots of dropped points, lowering this number may help. If you find an excess of noise in your project, increasing this number may drop more of the noise points. To start with, it is a good idea to leave the default parameters and create a point mesh to see what the output is like. You can then adjust them to optimize the output to your liking. The meshing options on this tab are covered in a later tutorial. Before meshing, you will need to generate a good point cloud, so the options are off by default. We hit Execute to create our first point mesh. PhotoModeler Scanner processes the photo pairs, and you can see a summary of what's being processed over here. We'll skip ahead to after the point mesh has been created. How long the point mesh takes to create depends on the amount of RAM, your CPU speed, the resolution of the photos, and your DSM settings. DSM processing is finished running, and we can see a point mesh has been created of 2,650 points. Open up a 3D view. turn on the point mesh options. We can see the point mesh that has been generated. To help visualize the mesh, we can turn on textures and the point cloud will be colored with values taken from the first photo of the pair. You can see how the mesh matches the data in the photos and extracts the depth for each point in the pair. Our point mesh has been created with little or no noise, which indicates the settings used were correct. We can go back to our dense surface dialog and increase the sampling rate to give us a higher density model. A point mesh with our new sampling rate has now been created with 3,000 points. You can see our new mesh over here. From this view, you can see there are holes in the mesh. This is because these areas are not visible on both photos. If you view the mesh from a similar angle as the photos were taken, you can see how all areas visible are accounted for. If we had taken photos from this angle, it would have included data in the gaps, but we would have other gaps on the far side. Images taken directly from above may provide data for all areas of this particular shape, but another technique is to include more than one set of stereo photos. This is covered in the multi-photo and troubleshooting tutorials. If your end goal is a triangulated mesh, holes like these can be filled in during triangulation, as covered in the triangulation tutorial. The raw point mesh data generated from photos will automatically be added to the raw point mesh layer, so it is easy to hide all non-triangulated point meshes. We will save this project as footprintdone.pmr. That concludes the PhotoModeler Scanner basic project tutorial. We have shown the steps to create a basic point cloud from 2 photos.